Now we move to the second part of the model fitting. First, I will review the least squares estimation presented in the previous video. Then I will talk about some extensions, including weighted least squares method and Hudson's continuous fitting algorithm, and also some details of Joinpoint software fitting options. The least squares method estimates the parameters by minimizing the sum of squared differences between the observed and expected responses. For Lehrman's grid search, we assume that the locations of join points are on the predetermined grid and search for the possible locations of the grid points at which the sum of squared error is minimized. Recall that one of the assumptions we have for the least squares fitting is that the variances of the responses are homogeneous over the time points, but it is often violated in practice. When this assumption is violated, subsequent inferences lose their accuracies. In such a situation, we can conduct the weighted least squares estimation. The same mean function as before, but we assume that the variance of the response at time xi is sigma I squared. That can be written as 1 over wi squared. The idea of the weighted least square estimation is to find the values of the parameters that minimize the weighted sum of squared differences. The weights are simply the reciprocal of the standard errors, which are used to stabilize the variance. Here is an example of Joinpoint input page. The first few lines of data will show up in the spreadsheet. For the dependent variable, there are various types that Joinpoint allows. And here are the default types provided in data file, age-adjusted rate. A user needs to select the dependent variable as well as independent variable. And there's an option that a user can choose for the variance covariance structure of the data. The first page also shows the basic model choice, either linear model or the log linear model. The log linear model is the default. Now I selected the rate for the dependent variable, year for the independent variable, sex for bivariable. If you click the down arrow for the heteroscedastic and correlated errors option, you will see several choices. The default is the standard error provided. When I kept the default or choose the standard error provided option, you can select the variable where the standard errors are stored. For this data set, it is the column under the heading of SE. I selected SE for the standard error provided. Below that is an option to handle correlated errors. The default is uncorrelated, and Joinpoint can handle autocorrelate data and also a general variance covariance matrix provided. Under the Method and Parameters tab, you can change various fitting parameters. For grid search, Joinpoint default settings are shown in this slide. For the grid search, we set the minimum numbers of observations in the end and middle segment as 2 and 2, And these minimum numbers exclude any join points that falls on a data point. These are set to calculate the standard errors of the estimated slopes. There's another box for the number of points to place between adjacent observed x values, for which default value is 0. This means that the default grid is the grid made with the time points in the dataset. If you put 1 here and you use the annual data, then the fit will be obtained over the half-year grid. The number of join points was set from 0 to 3 in this case. And the maximum number is determined according to the data length. A user can change these two values, for example, 1 and 2. For AAPC, average annual percent change rate, the default is the entire data range. But you can specify a range for which you like to get the AAPC estimate. This slide summarizes what I talked about, the ideas of grid search. Also, some remarks on the default setting. Other remarks. Although the implementation of the grid search algorithm is straightforward, a drawback of the grid search is that the location of a join point can only be at one of the grid points. Also, it can be computationally expensive. So we implemented a continuous fitting algorithm following Hudson, published in 1966, where the location of a join point can be anywhere in the data range. The idea of the Hudson's algorithm is to make a least squares fit for each segment in a given partition of the data and to make adjustment to the estimated join points. For example, consider the case with one join point. Fit the least squares lines for the partition x1 through xi and xi plus 1 through xn for each I. Find the intersection of the two least squares lines, call it tau tilde. If the intersection is in the right place, meaning that it is between xi and xi plus 1, use tau tilde as tau hat. Otherwise, make an adjustment for tau tilde to be in the right place. In our paper published in 2007, we described the details of the Hudson's continuous fitting algorithm and made computational efficiency comparisons. We observed that the basic grid search is more efficient than the Hudson's algorithm in general. But Hudson's algorithm is more efficient than the grid search with one midpoint between the data x values. Hudson's algorithm is computationally more efficient than fine grid searches and provide more accurate and efficient point and interval estimates of the model parameters. For example, this table shows confidence intervals for the locations of join points obtained by the annual research as well as Hudson's method. And we see that Hudson's method produces narrower confidence intervals. However, Hudson's algorithm is computationally less efficient than the basic research. Here are the references. Thank you.
U.S. Department of Health and Human Services, National Institutes of Health, National Cancer Institute, cancer.gov, 1-800-4-CANCER.